Water has been discovered on a world where its presence is highly improbable. GJ486b, a scorching super-Earth, lies merely 26 light-years distant. It completes an orbit around its star in under 2 days, subjected to radiation so powerful it could strip a planet bare. Nevertheless, the James Webb Space Telescope revealed the distinct spectral fingerprint of water on this celestial body. This unambiguous and surprising finding compels us to reevaluate the evolution of rocky planets when exposed to intense heat, and what substances they might still manage to retain. If this interests you, subscribe and join our quest as we unveil the universe's messages and narratives inscribed among the stars. Prior to any inkling of an anomaly within this system, astronomers initially observed a tiny, dim star shining subtly within the Virgo constellation. This was a red dwarf, the most prevalent type of star found in our galaxy. Being smaller, cooler, and less luminous than our sun, these stellar bodies consume their fuel at a leisurely pace. Consequently, their lifespans extend for trillions of years. Throughout the entire cosmic history, no red dwarf has yet reached an advanced age, their constant luminosity. Unassuming in their look, and this particular one, situated approximately 26 light-years distant, appeared indistinguishable from countless others of its kind. For an extended period, it gave no indication that anything noteworthy was concealed in its vicinity. While red dwarfs can exhibit activity and unpredictability, this particular star seemed tranquil. Researchers examining its luminosity detected only minor fluctuations, attributed to its gradual rotation and magnetic regions. No evidence suggested the existence of a proximate planet until a minuscule decrease in the star's illumination became visible. It was so faint it nearly merged with background interference. However, it reappeared consistently, recurring every 1.47 days. Such a regular pattern could signify only a single phenomenon. A celestial body was transiting across the star, obstructing a small portion of its light with each passage. Based on the magnitude of this dimming, scientists calculated the planet's radius, approximately 1.5 times that of Earth. Subsequently, they quantified the star's subtle oscillation, which was induced by the planet's gravitational pull. This oscillation disclosed the planet's mass, which was roughly 3 times that of Earth. Combining these figures indicated that this world possessed extraordinary density. Composed primarily of rock and metallic elements, it constituted a super-Earth, more massive than our own planet, yet remaining solid and highly compact. With gravity almost 3 times more potent than Earth's, each stride would feel akin to repeatedly hoisting your own body weight. The orbital path presented the subsequent astonishment. The planet completes its circuit around its star in under 40 hours. Its full year elapses more quickly than a single weekend on Earth, were it situated within our solar system. The planet's orbital path would easily fit within Mercury's trajectory. At such proximity, free rotation is impossible, as tidal forces keep one side of the world perpetually oriented towards its star, while its opposing face stays in perpetual shadow. This divides the planet into 2 distinct halves, a scorching hemisphere bathed in endless daylight, and a frigid counterpart that never experiences the star's light whatsoever. The sun-facing side absorbs roughly 70 times the energy that Earth receives from its own sun. Temperatures can soar to approximately 430 degrees Celsius, which is around 800 degrees Fahrenheit. This heat is sufficient to liquefy numerous metals. Rocks radiate warmth, and the surface could feature reservoirs of molten lava. Any atmosphere, should it be present, would appear to waver and warp due to the intense heat. Even robust substances would lose strength and contort, given these circumstances. Concurrently, the night side experiences a dramatic drop in temperature, lacking any solar illumination. It transforms into a quiet, icy terrain. Should a tenuous, gaseous layer envelop the planet, winds would surge from the illuminated to the dark side at astonishing velocities, propelled by the vast disparity in temperature. However, if the planet possesses no atmosphere whatsoever, the divergence would be complete. A furnace on one side, e congelador no outro, pois a estrela bombardeia o planeta com radiação, particularmente luz ultravioleta. Os cientistas antecipavam que o planeta estaria totalmente desprovido de ar. Os raios ultravioleta desintegram moléculas em um piscar de olhos. O hidrogênio foge para o espaço e os átomos mais densos se depositam na crosta ou interagem com a superfície. Across countless millennia, this mechanism eradicates any semblance of an atmosphere. Consequently, when celestial observers initially intended to study this planet using the James Webb Space Telescope, they anticipated a straightforward outcome, an unblemished, level spectrum displaying no indications of gas whatsoever surrounding the planet. Indeed, this formed a component of the design. This world was selected as an experimental subject, a reference point. Webb's apparatus possesses exceptional sensitivity, and researchers had to verify its capacity to ascertain a genuine lack of atmospheric characteristics prior to seeking evidence of life on more diminutive, colder celestial bodies. A parched super-Earth, devoid of an atmosphere, appeared to be the ideal calibration instrument. Yet, nature frequently declines to conform precisely to predictions. The world's core could remain dynamic due to tidal warming, a result of the continuous elongation and compression induced by its constricted orbital path. This process has the potential to liquefy rock far beneath the surface, forming magma pockets and initiating volcanic activity on Earth. On this hotter, more massive world, volcanoes discharge gases from the mantle, among them water vapor. This identical process might unfold on a considerably grander scale. If water is confined within minerals in the planet's crust or mantle, intense heat has the capacity to release it as vapor. Volcanic vents, surface fissures, or even molten rock could transport this vapor upwards in a location where the star is perpetually removing gas. Such vapor would not establish a stable atmosphere. Instead, it would ascend only momentarily, be observed during transit, and rapidly dissipate. This would form a delicate, transient, gaseous layer. Instead of a full atmosphere, it would be a delicate stratum continuously renewed by geological processes and eradicated by radiation. The star itself introduces an additional layer of complexity. Red dwarfs frequently possess cooler areas on their surfaces, termed star spots. Within these colder zones, molecules, including water vapor, are capable of surviving. Should the planet traverse one of these spots during transit, the star's inherent water may manifest in the spectrum, imitating the signature of a planetary atmosphere. Both scenarios, a genuine atmosphere or stellar contamination, can yield almost identical signatures. Differentiating between them represents one of the most formidable challenges in exoplanet science. Yet the fundamental expectation appeared solid. The planet should have shed all its volatile compounds ages ago, with no atmosphere remaining. No water was expected to persist either on or above its surface. This rendered the subsequent findings all the more astonishing when Webb observed multiple transits. It gathered thousands of measurements of the starlight that traversed past the planet. These readings were subsequently resolved into a light spectrum, divided into distinct wavelengths. For a barren rock devoid of an atmosphere, the spectrum ought to have appeared smooth and featureless, instead of the anticipated blank spectrum. Scientists anticipated Webb detected a dip at 1.4 microns. This anomaly manifested not just once, but across numerous transits. Each time it persisted through every calibration procedure intended to eliminate noise or instrumental drift. The characteristic was minor, yet its consistency rendered it impossible to disregard. That specific wavelength corresponds precisely to the region where water vapor absorbs infrared light. Observing this phenomenon around such a hot and exposed world contradicted almost every existing model for atmospheric persistence near red dwarfs. Extreme heat ought to annihilate water instantly, and ultraviolet radiation should strip away any lingering fragments long before a telescope could register their presence. Nevertheless, the indication persisted, subtle yet constant and undeniably authentic. Its existence prompted inquiries. These were questions no one had anticipated. Was the vapor originating from the planet itself, perhaps released through volcanic fissures? Alternatively, was it being expelled from minerals on the scorching sunlit side? Or might it instead be forming in cooler star spots on the red dwarf, thereby generating a misleading signal, which merely resembled an atmosphere? Or was the system concealing a completely novel process that existing models had overlooked? To address these inquiries, researchers were now compelled to scrutinize both the star and the planet with significantly increased diligence, charting their reciprocal influence and learning to distinguish the planet's unique markers from those of the star itself. This enigma necessitated a more thorough investigation into how telescopes interpret starlight and how even the most subtle anomalies can unveil the reality of faraway celestial bodies. To grasp why the detection of water in this particular system proves so challenging to decipher, we must examine how telescopes perceive light. Worlds revolving around faraway stars are not directly observable, neither their surfaces nor their forms. Rather, their existence must be deciphered from minute alterations in starlight, much like a fingerprint can be identified even when gently pressed against glass. This technique, referred to as transit spectroscopy, stands as one of the most potent instruments available to astronomers for investigating remote celestial bodies. However, it also necessitates exceptional precision. Every minute aspect of the light is significant, and even the slightest aberration can alter the complete narrative. As a planet traverses before its host star, the star momentarily darkens. This reduction in brightness informs astronomers of the planet's dimensions, yet simultaneously, a minute portion of the starlight passes through the material enveloping the planet, be it its atmosphere, if present, or the exposed region above its surface. Should it lack an atmosphere, molecules within that vicinity absorb highly specific wavelengths of light. Water vapor, for instance, exhibits strong absorption near 1.4 microns. Carbon dioxide possesses its distinct range of wavelengths, as does methane, oxygen, and various other molecules, each leaving unique imprints. When Webb disperses that starlight into a spectrum, these characteristic patterns manifest as minor depressions, resembling indentations carved into a light beam. For colossal planets such as Jupiter, these indentations are readily discernible, owing to their dense atmospheres, which imbue the spectrum with pronounced characteristics. However, for diminutive rocky worlds, the signals are considerably fainter, at times measuring merely a few dozen parts per million. Identifying these subtle indications demands impeccable timing, exceptional stability, and precise calibration. Even a minor tremor of the telescope, a gradual alteration in temperature, or an influx of cosmic rays has the potential to corrupt the data. Webb was engineered to manage these difficulties. However, their interpretation is always complex. This challenge intensifies when the parent star is a red dwarf. These celestial bodies are diminutive and cold, yet their surfaces are highly irregular. Frequently, they feature colder regions known as star spots, which are zones influenced by magnetic fields where temperatures can decrease sufficiently for molecules to form, such as water vapor. To an observer, light emanating from a star spot exhibits distinct spectral characteristics, signatures compared to light from the star's other areas. Should a planet traverse one of these colder regions, the alteration in stellar light might mimic the existence of water surrounding the planet, even if no water is actually present. This intermingling of stellar and planetary signals renders red dwarf systems among the most challenging to decipher within the entire field of exoplanetology. This explains why the unanticipated water trace detected near the planet sparked such a vigorous discussion. The observed signal was genuine, but its significance remained unclear. In order to evaluate the various possibilities, researchers commenced by analyzing the temporal aspect of the 1.4 micron dip. Were water vapor to envelop the planet, the absorption would manifest solely during the transit event. If its origin was the star, residual signs could persist even prior to or following the passage, contingent on the star's rotational speed and the spot's dimensions. Within Webb's collected data, the signal's peak clarity occurred during the transit. However, subtle indications of absorption stretched a little past this period. That uncertainty allowed both hypotheses to remain viable, necessitating further proof. Subsequently, astronomers developed elaborate models depicting the potential behavior of the star. They simulated various configurations of star spots, some expansive, others dispersed, and some encompassing merely a small percentage of the surface. A significant number of these models generated a dip, almost indistinguishable from the one observed by Webb. This implied that the star itself could be the sole cause. Nevertheless, scientists also modeled tenuous planetary atmospheres, incorporating situations where atmospheric gases were continuously depleted and renewed through volcanic processes. These particular models likewise corresponded with the collected data. The issue wasn't that one hypothesis provided an inadequate fit. Rather, both aligned perfectly. To resolve this impasse, astronomers required observations across additional wavelengths. Water exhibits varying behaviors throughout the infrared spectrum. At shorter wavelengths, the absorption of planetary water becomes less pronounced, whereas stellar water absorption intensifies. Webb's initial instrument only encompassed a segment of this range. To comprehend the complete profile of the dip, the telescope was required to observe further transits. By employing its secondary infrared spectrograph, which extends into spectral regions inaccessible to the primary instrument. While these forthcoming observations were being arranged, investigators scrutinized the physical processes potentially occurring above the planetary surface. Were the water's characteristic traced to have originated there, it wouldn't derive from oceans or clouds, given that the conditions are much too mild for such a setting. Instead, it would arise from vapor expelled from minerals by intense heat, or from steam discharged through volcanic fissures when the star's radiation strikes these molecules. Hydrogen escapes into space while oxygen adheres to the surface. This process rapidly depletes the upper atmosphere, but if the interior continues to release fresh vapor, a delicate, continuously replenished layer might emerge during each transit. Such a stratum would be exceptionally fragile, akin to a veil rather than a full atmosphere. However, even a mere veil can leave discernible traces in starlight. A further question was whether the planet could be heated internally by tidal forces. Its orbit is somewhat elliptical, meaning its distance from the star varies over time. As it alternately approaches and recedes, gravitational forces cause the planet's interior to stretch and contract. On Jupiter's moon Io, this process powers the most potent volcanic eruptions in the solar system. On a world with 3 times Earth's mass, this effect could be considerably more pronounced. This would melt deep rock layers and create passages through which gases could escape. If water or hydroxyl compounds are trapped within the mantle, they might ascend as vapor, thereby replenishing the thin envelope above the surface. However, none of this guarantees that the signal originates from the planet. The star remains a compelling alternative. Red dwarfs frequently host molecular regions that shift across their surfaces. As they rotate, vapor within these cooler patches can mimic an atmospheric signature with such precision that even a highly sensitive telescope may struggle to differentiate the two. This is why understanding the star, its spots, its temperature fluctuations, and its magnetic cycles is just as important as studying the planet itself. To monitor the star's behavior, ground-based telescopes monitor its brightness in visible light. Star spots appear darker at those wavelengths, so changes, in that data help scientists map the location of spots and how they move. By comparing this information with Webb's infrared observations, researchers can determine whether the 1.4 micron dip changes as the star rotates. If it does, the star is the source. If it remains constant, the planet is the more probable culprit. Despite these efforts, a layer of uncertainty still exists. The science is challenging, not because the instruments are weak, but because the signals are faint enough that both the star and the planet can leave nearly identical marks. It's akin to listening to 2 people whisper in the same room, their voices blending. Distinguishing them requires meticulous attention. This system, once deemed straightforward, has evolved into a crucial training area for exoplanetary science. It instructs investigators on how to interpret signals that are barely discernible. It compels them to validate their models, challenge their presumptions, and perfect each stage of their analytical process. The insights gained here will influence the manner in which astronomers will interpret information from cooler, more terrestrial planets in the coming years. Webb's subsequent observations are intended to furnish the absent component, the gradient of the water signature across an expanded spectrum of wavelengths. Should the attenuation diminish at shorter infrared wavelengths, the vapor probably envelops the planet. If it intensifies, the cooler areas of the star are the cause. Consequently, the investigation proceeds driven by the concept that veracity resides not in an isolated measurement, but in the coherence of all of them combined. The observatory must re-examine. The stellar body requires more meticulous mapping. The planetary body must be assessed under varying circumstances. Only then will scientists be capable of confidently asserting whether the water signature originates from the parched world, beneath, or from the subtly active star that heats it. To comprehend if water could genuinely persist around such an extraordinary planet, researchers were compelled to envision the world not merely as a data point, but as an environment sculpted by thermal energy, gravitational forces, and perpetual conflict. Even at a distance of 26 light-years, the physical properties portray a striking image. Every aspect of this planet is driven to its utmost boundaries, well beyond anything Earth has ever experienced. Its most prominent characteristic is the intense heat, as the planet's orbit is so proximate to its red dwarf that it is gravitationally locked. One hemisphere perpetually confronts the star, while the opposing side remains in perpetual shadow. On the illuminated hemisphere, temperatures attain approximately 430 degrees Celsius, a heat level sufficient to compromise metal and induce rock to incandesce. The star remains fixed, never descending below the horizon. It merely hovers directly above, inundating the terrain with radiation. The surface likely fissures due to thermal strain, and any substance subjected to prolonged exposure would either sublimate or liquefy. Gravitational pull exacerbates the severity. Possessing a mass approximately 3 times that of Earth, the planet's superficial layer. Gravitational force exerts considerable pressure. Locomotion would seem arduous and deliberate, and even a tenuous atmosphere would adhere closely to the terrain. Elevations would be diminished, molten rock would extend further, and particulate matter would rapidly deposit under the unyielding attraction. Nevertheless, notwithstanding these arduous superficial circumstances, the world might not be geologically inert. Its orbital path is not perfectly spherical. Each instance, it shifts marginally nearer to or further from its stellar body. Gravitational forces distend and contract its internal structure. This phenomenon of tidal heating is identical to the mechanism that powers the volcanoes on Jupiter's satellite Io. Portions of the mantle might melt, forming magma chambers below the crust. Should these chambers breach the surface, volcanic openings and cracks could emit gases, such as water vapor held within minerals deep inside the planet. Nevertheless, any vapor ascending into the higher atmosphere is instantly destroyed. Ultraviolet light rapidly splits water molecules, causing hydrogen to escape into space, while oxygen binds to a heated surface. For water vapor to be detectable in Webb's observations, it must be continuously resupplied. This indicates an internally active world that consistently emits minor quantities of gas into space. The planet's night side presents a contrasting scenario. Being perpetually protected from stellar light, it grows significantly colder. Minerals solidify, and errant gases migrating from the warmer hemisphere might settle or freeze. Should the planet have even a tenuous exosphere, winds would transport matter from the intensely heated day side to the frigid night, thereby establishing an unusual cycle of warming, chilling, and expulsion. This particular cycle would not generate a conventional atmosphere, yet it could sustain a subtle amount of vapor for a sufficient duration to be observed. Situated between these two opposing conditions is the terminator, the band of twilight encircling the world. Here, temperatures range from intense heat to profound cold, forming a confined area where rock alternately shrinks and swells with every alteration in internal pressure. Extensive fissures might develop along this region, providing conduits for gases to escape. If vapor is present in measurable quantities anywhere above the surface, the twilight zone could be its primary concentration point. These environmental differences are vital, as Webb doesn't directly view surfaces. Instead, it gauges how starlight alters when the planet transits its star. Should vapor primarily emanate from vents or cracks, the resulting signature won't be entirely consistent. Minor irregularities in the absorption spectrum might emerge, providing clues regarding the vapor's distribution. The signal's configuration effectively maps out the planet's venting locations and where it experiences loss. However, despite all the persuasive planetary explanations, the host star presents an equally plausible possibility. Red dwarfs inherently produce water vapor within their cooler stellar spots. Should the planet traverse one of these spots, the subsequent alteration in starlight can precisely imitate the characteristic signature of an atmosphere. Differentiating between these two scenarios necessitates examining various wavelengths. Water originating from the planet diminishes at shorter infrared wavelengths, whereas stellar water intensifies. Webb's secondary spectrograph, which operates across a wider spectrum, will be crucial for verifying the signal's source. As preparations for those upcoming observations proceed, scientists are examining additional evidence. A particularly significant clue stems from the planet's secondary eclipse, the instant it passes behind its star. This enables astronomers to directly ascertain the planet's dayside temperature. The outcome: thus far, the emissions align with those expected from a barren rock exposed to continuous illumination, implying any atmosphere present must be exceedingly tenuous, much too insubstantial to retain warmth. Nevertheless, a slender atmospheric layer differs from a complete absence. Mercury, for instance, sustains a tenuous exosphere. Composed of atoms dislodged by radiation and tiny meteoroids, a comparable, fragile stratum might exist on this world. This layer is perpetually eroded and continuously replenished. The internal composition provides further clues to the enigma. A planet's density suggests the presence of a substantial iron core. Encased by a silicate mantle, these silicate minerals possess the capacity to retain water far beneath the surface, discharging it upon exposure to elevated temperatures. Should tidal forces maintain portions of the mantle in a molten state, this expulsion might persist for billions of years. In this regard, the world could function akin to a pressure cooker, sealed, heated, and intermittently releasing vapor. However, the most significant obstacle is still the star. Red dwarfs exhibit high activity. Their surfaces are prone to rapid transformations. Even one flare has the potential to modify the quantity of molecular vapor within the stellar atmosphere. Stellar spots move into and out of sight. To observe these shifts, terrestrial telescopes observe the star using visible light, charting its luminosity and identifying cooler areas. Each variation in the star's light serves as an indicator, assisting investigators in ascertaining if the detected water signature originates from the planet or the star. Ultimately, this celestial body is not merely scorching or inhospitable. It is a dynamic entity, influenced by internal warmth and external radiation, caught between stellar erosion and replenishment from its own core. Its sunlit hemisphere is ablaze, while its nocturnal side is frozen. Furthermore, its transitional twilight zone might serve as a confined passage through which gases dissipate into the cosmos. The origin of the observed water network, be it from volcanic steam, mineral vapor, or stellar spots, is still unclear, yet every potential source provides enhanced insight into the conduct of rocky planets when subjected to circumstances vastly exceeding those encountered within our own solar system. With the impending commencement of the subsequent observation phase, scientists are aware that this world has already broadened the scope of what rocky exoplanets are capable of being. It is instructing them on the mechanisms by which atmospheres endure or collapse under unyielding heat, how stellar illumination can mimic planetary air, and how even the most subtle trace can fundamentally alter our comprehension of remote celestial bodies. The enigma endures, but with each subsequent measurement, the world unveils a bit more of the narrative it has preserved across billions of years in space. A researcher sought the origin of the water signal. Focus reverted to the star, as if the planet struggled to retain water, then conceivably the star itself was generating the semblance of an atmosphere. To delve into that potential, astronomers needed to comprehend the star not merely as a basic light point, but as a dynamic, a constantly evolving surface. What looks serene from 26 light-years distance is, nearby, an area formed by magnetic disturbances, varying temperatures, and chemical processes that can readily confound even the most sophisticated telescopes. Although red dwarfs are often small, their magnetic fields can be robust and complex. Such fields give rise to cooler zones termed star spots, which may encompass substantial areas of the surface. In these colder sections, molecules that typically disintegrate in the star's intense heat, including water vapor, can both form and persist. This one particularity transforms the entire perspective. As water vapor within a star spot is capable of generating absorption characteristics at the identical wavelengths that planets utilize to unveil their atmospheres. When a planet passes over one of these cooler zones, the modification in starlight can precisely resemble water surrounding the planet. This phenomenon is highly persuasive, since telescopes are incapable of directly viewing star spots. They solely perceive how the light alters when the planet obstructs distinct sections of the star. If the planet transits a bright area, the dimming seems ordinary, but if it crosses a star spot that contains water vapor, the spectrum alters in a manner that mirrors a planetary signature. The outcome is smooth and, in some situations, virtually impossible to differentiate from an atmosphere. The water signature Webb detected displayed clues of this characteristic. The drop at 1.4 microns was authentic and recurred. However, the boundaries lacked perfect smoothness. Planetary atmospheres generally produce clear, rounded characteristics, while stellar water frequently produces forms that are somewhat irregular or distorted by turbulence. Webb's observations landed somewhere between these two potential scenarios, thereby making the outcome even more difficult to decipher. For investigation, astronomers analyze the star's rotation. It completes one revolution every 100 days, a leisurely pace for a red dwarf, indicating that star spots shift slowly. If the water signal's intensity altered over several transits, this rotation might aid in uncovering its origin. Initial data offered ambiguous indications. Slight variations implied that something on the star could be influencing the signal, though insufficient for outright confirmation. Ground-based telescopes contributed another element to the enigma by observing the star in visible light. They monitored subtle brightness alterations caused by star spots. The fluctuations were slight, but they verified the presence of star spots. This indicated that the star could, at least in principle, replicate the planet's water signature. To examine this hypothesis, scientists developed intricate computer models simulating numerous star spot configurations, vast dark regions, thin strips, dispersed fields. Many of these yield spectral characteristics. The detected object is almost identical to Webb's finding, though models of a thin, continuously replenished planetary atmosphere similarly correspond with the data. The system, yet again, failed to provide a singular, unambiguous explanation. The subsequent step involved examining how light behaves when it passes through a red dwarf. On the star's surface, convection patterns slowly ascend and descend, transporting heat upwards and pulling magnetic fields along with them. Such patterns generate regions of differing temperatures, which impact how molecules form and dissolve. When coupled with the planet's shadow during transit, these fluctuations produce a blend of signals that necessitate separation with utmost precision. Among the most potent instruments for accomplishing this is the wavelength slope test. Water present in a planetary atmosphere diminishes in strength at shorter infrared wavelengths. Conversely, water within a stellar spot intensifies. Webb's initial instrument observed one segment of the spectrum, whereas its second instrument, NIRISS, is capable of observing the remaining portion. Only by observing how the dip behaves across this broadened range can scientists definitively ascertain whether its origin is planetary or stellar. This particular observation constitutes a primary objective for the upcoming data cycle. In the interim, astronomers persist in monitoring the star's flare activity. Red dwarfs frequently generate abrupt, powerful eruptions of ultraviolet radiation. A solitary flare has the potential to modify the chemical composition of the star's upper strata or shift the arrangement of star spots. Should a flare occur prior to or during a transit, the spectrum might shift sufficiently to either imitate or obscure molecular features. Consequently, timing becomes paramount. Every observation requires comparison with the star's activity to guarantee that the data remains undistorted. An additional promising indicator originates from secondary eclipse data, the instances when the planet transits behind the star, rendering only the star's illumination visible. Should the water signal manifest during the eclipse, its origin must be stellar. If it vanishes, the planet continues to be a strong candidate. Initial eclipse measurements suggested minor distinctions, however. The signal proved too weak to permit definitive conclusions. Further observations are required. This challenge underscores the extent to which exoplanet research has progressed. Just a decade prior, identifying any atmospheric signature from a rocky planet of this diminutive size would have appeared unfeasible. Webb's advancements altered this by extending sensitivity to unprecedented boundaries. Yet this heightened sensitivity introduces a new challenge. Stars themselves have become sufficiently intricate to mimic planets. What was once perceived as a straightforward measurement now encompasses multiple layers of detail, influenced by the star's intrinsic behavior. Nevertheless, comprehending these stellar phenomena remains crucial for future endeavors. The majority of planets that might eventually exhibit indications of life, should they orbit red dwarfs, scientists risk being unable to reliably distinguish stellar interference from genuine atmospheric indicators in this context. They might misinterpret data from more Earth-like planets in the future. This particular system serves as more than just a conundrum. It provides preparation for future findings. Ultimately, the star has emerged as a key player in this narrative. It is not simply a background for the planet, but rather an engaged entity able to influence the light arriving at Webb, regardless of weather. The water signature originates from the star or the planet. The method of revealing this truth is altering how celestial observers interpret stellar light. And while Webb gets ready for its vital subsequent observations, the system remains a single star, a solitary scorched world, and an enigma that has already propelled exoplanetary research into an unprecedented age of accuracy. To ascertain if the water signature originated from the star or the planet, researchers were compelled to delve further into the methodologies enabling instruments such as Webb to decipher the cosmos. Initially, starlight appears straightforward, a constant radiance traversing the void. However, when that illumination interacts with a world, an atmosphere, or even a sunspot, it transforms into something considerably more intricate. It evolves into a communication, encoded in patterns so subtle that only the most rigorous examination can disclose their meaning. Comprehending the enigma surrounding this warm celestial body necessitated understanding how that communication is interpreted. Each piece of data collected by Webb commences with a minor alteration in luminosity. When the planet traverses before its star, the overall light diminishes by under 0.1%. This minuscule reduction establishes the fundamental level of a transit. Yet, embedded within that decrease are even more minute fluctuations, alterations merely dozens of parts per million in depth, which contain hints about atmospheric compounds, surface activities, and the conduct of the star itself. To identify something as subtle as a water fingerprint, such subtle fluctuations need to be isolated from background noise, thermal shifts, electrical disturbances, and even the slight enlargement and shrinkage of the instrument itself. The procedure commences by splitting the stellar light into thousands of fine wavelengths, a method known as spectroscopy. Every wavelength acts akin to a book page. Some pages are empty while others exhibit dark markings or absorption characteristics, where molecules have captured minute segments of the illumination. Water vapor exhibits strong absorption close to 1.4 microns, resulting in a clear depression in the spectrum. Webb observed this dip, but the difficulty lay in determining its origin, the star or the planet. Distinguishing between the two necessitates comprehending how the spectrum evolves temporally when the planet is not positioned in front of the star. The light exclusively carries the star's unique imprint. Once the transit commences, the planet obstructs a portion of the star, and the spectrum then becomes a blend of the stars and the planet. By contrasting observations from before, during, and after the transit, scientists are able to pinpoint the planet's specific contribution alone. However, if the star itself contains water vapor within its cooler zones, even this comparative analysis becomes indistinct. The absorption characteristic manifests irrespective of any planetary contribution. Consequently, due to this, scientists depend on timing as much as on wavelength. Planetary absorption should manifest solely during transit, vanishing almost instantaneously. Once the planet moves away from the star, stellar absorption behaves differently. It persists, slowly drifting, as stellar spots rotate across the star's surface. When Webb's data hinted at residual absorption after transit, it failed to provide an answer. It merely intensified the ambiguity. The pattern was subtle enough to align with either scenario and too small for anything but more precise measurements to untangle it. One of the most potent methods to break this tie involves analyzing how different wavelengths behave concurrently. Planetary atmospheres do not absorb uniformly across the spectrum. At shorter infrared wavelengths, water becomes less efficient at blocking light. Conversely, for water inside a star spot, the opposite holds true. Cooler regions imprint stronger absorption at shorter wavelengths. The precision of this slope difference is such that even a slight change across the spectrum can reveal the true source. Webb's initial observations did not stretch quite far enough to measure the full slope, but NIRISS, the next instrument in line, will. It observes wavelengths where the two possibilities diverge most significantly, making it a crucial step in solving the puzzle. While preparing for those observations, scientists refine their data pipelines. Instrument drift, tiny shifts in detector sensitivity can mimic weak absorption lines. Cosmic rays striking the detectors can create spikes in brightness that must be removed without erasing genuine features. Even the telescope's orbit causes temperature fluctuations that slightly modify the spectrum's shape. Every effect must be mapped, modeled, and corrected before the data can be trusted. Teams around the world use independent methods to cross-check each other's results when all pipelines converge on the same feature at the same. Confidence based on wavelength data strengthens that the signal is genuine, though its true nature in this instance is still attributed to two distinct origins, leading astronomers to adopt a different approach, analyzing the planet's thermal radiation when it transits behind its star. During a secondary eclipse, the star's illumination overwhelms the signal. By contrasting the spectrum observed before and during the eclipse, scientists are able to estimate the quantity of light the planet radiates from its sunlit side. This thermal output provides insights into surface conditions. A substantial atmosphere would redistribute warmth, thereby diminishing the temperature difference between day and night. However, the measured heat aligns nearly perfectly with what an exposed rock would undergo. The planet radiates energy like a hot, solid surface with scant insulation. This does not completely exclude the existence of an atmosphere, though it confines it to an exceedingly thin layer. Nevertheless, even a slender envelope can be significant. Trace gas hovering above the scorching surface is still able to interact with starlight during its transit, even with just a few microbars of pressure. A pressure thousands of times lower than Earth's atmosphere can generate a detectable absorption line if the gas contains the appropriate molecules. If water is released by volcanic vents or heated minerals, uninterruptedly, even in minute quantities, the planet might appear to possess an atmosphere to a remote observer. For short durations, Webb may have captured one of these instances. Some models propose that thermal desorption, water escaping from heated minerals, could provide vapor more rapidly than stellar radiation eliminates it. In this particular scenario, the day side functions as a massive kiln. Minerals expand, release vapor, and then cool once more as the planet rotates. Under the star's intense illumination, the vapor ascends, briefly interacts with light, and is then carried away into space. Its existence is brief, yet it is detectable. Other models center on volcanic activity. If the planet's interior remains molten, pressurized magma reservoirs could emit gases through fissures in the crust. Io, Jupiter's volcanic moon, illustrates the potency of tidal heating even on a considerably smaller body. If analogous forces are present here, they could maintain the interior, sufficiently active to provide a slender yet continuous stream of vapor. Still, every atmospheric explanation demands a delicate equilibrium. The water emitted must correspond to the rate at which radiation eliminates it. Too little, and the signal vanishes. Excessive amounts and the planet's temperature would appear distinct from what Webb observed during the eclipse. The narrow margin of that balance is why many researchers favor the stellar hypothesis, as it aligns more naturally without needing any unique conditions. Merely star spots, which are anticipated on red dwarfs. However, the stellar theory also prompts further inquiries if water vapor exists within the star's atmosphere. This indicates that specific areas attain sufficiently low temperatures for molecules to persist, offering an uncommon laboratory for investigating the chemistry within red dwarfs. It might aid in improving stellar models utilized throughout astronomy, ranging from exoplanet research to galactic development in this regard. Even an explanation centered on the star propels the field forward. The challenge isn't due to instrument or model shortcomings. It merely reflects the intricate nature of the cosmos. when observed with sufficient precision. What previously seemed like a clear distinction between planet and star now manifests as a complex interaction of light and heat, where one component can mimic the other. Webb possesses enough power to uncover these nuances, and in doing so, it has brought to light difficulties that no prior telescope faced. As preparations proceed for the subsequent series of observations, the system remains in a state of scientific anticipation. The planet orbits its star every 40 hours, with each revolution presenting another chance for its atmosphere, or lack thereof, to become apparent. The star keeps rotating gradually, its surface patterns altering sufficiently to modify the spectrum every month. And Webb awaits the ideal alignment, poised to capture the illumination that will ultimately decide the matter of whether the water signature pertains to the planet or the star. This inquiry has already transformed the methods scientists employ to examine small, rocky exoplanets, proved to be considerably more intricate than anticipated, and stars significantly more impactful on how their planets are perceived. Deciphering these interwoven signals isn't merely a move toward resolving a single enigma. It forms a basis for comprehending every rocky world Webb will investigate in the upcoming years. To ascertain if the water signal originated from the star or the planet, researchers needed to delve further into the methodologies that enable telescopes such as Webb to interpret the cosmos. Initially, starlight appears straightforward, a constant radiance traversing space. However, when that illumination interacts with a planet, an atmosphere, or even a stellar spot, it transforms into something considerably more intricate. It turns into a message inscribed with patterns so subtle that only the most rigorous analysis is capable of disclosing their meaning. Grasping the enigma surrounding this warm world necessitated understanding how that message is deciphered. Each piece of information Webb collects commences with a minor alteration in luminosity as the planet transits before its star, the overall light. The dip is less than 0.1%. This minuscule decrease represents the transit's baseline, but even tinier variations are embedded within that drop. These alterations, only a few dozen parts per million in magnitude, contain vital clues regarding atmospheric molecules, surface processes, and stellar behavior. To identify a water signature, which is incredibly subtle, those faint variations must be distinguished from noise, temperature drift, and electronic interference. This includes even the slight expansion and contraction of the telescope itself. The procedure commences by splitting the starlight into thousands of narrow wavelengths. Through a method known as spectroscopy, each wavelength functions like a page in a book. Some pages are blank, but others feature dark lines. These are absorption features, signifying where molecules have intercepted minute portions of the light. Water vapor absorbs intensely near 1.4 microns. This leaves a distinct dip in the spectrum. Webb detected that dip, but the challenge was to ascertain its source. Was it the star or the planet? Differentiating between the two necessitates understanding the spectrum's changes. This occurs over time. When the planet is not positioned before the star, the light contains only the star's unique signature. Once the transit commences, the planet obstructs a section of the star, and the spectrum then becomes a blend of both the star and the planet. By comparing observations from before, during, and after the transit, scientists are able to isolate the planet's unique contribution. However, when the star itself contains water vapor within its cooler regions, even this comparison becomes indistinct. The absorption feature manifests whether or not the planet contributes anything. Due to this, scientists depend on precise timing. Timing is as crucial as wavelength. Planetary absorption should only be visible during transit, disappearing almost instantly once the planet moves away from the star. Stellar absorption, however, behaves differently. It persists, slowly drifting as star spots rotate across the star's surface. When Webb's data indicated a trace of residual absorption after transit, it did not provide an answer. Instead, it merely deepened the ambiguity. The pattern was subtle enough to fit either scenario, and sufficiently small that only more precise measurements could resolve it. One of the most effective ways to break this tie involves analyzing the simultaneous behavior of different wavelengths. Planetary atmospheres do not absorb uniformly across the spectrum. At shorter infrared wavelengths, water becomes less effective at blocking light, But for water located within a star spot, the reverse is true. Cooler regions exhibit stronger absorption at shorter wavelengths. This difference in slope is remarkably precise. A minor alteration throughout the spectrum has the potential to uncover the actual origin. Webb's initial observations, however, did not extend sufficiently to quantify the complete gradient. Nevertheless, the subsequent instrument, NERIS, is designed to do so as it monitors wavelengths where the two potential outcomes differ most significantly, thereby establishing it as a vital stage in resolving the enigma. In anticipation of these observations, researchers meticulously enhance their data processing systems. Minor fluctuations in detector responsiveness, known as instrument drift, are capable of simulating faint absorption lines. Furthermore, cosmic rays impacting the detectors may generate abrupt increases in luminosity, which necessitate removal without inadvertently eliminating authentic characteristics. Even the orbital path of the telescope induces variations in temperature, which subtly modify the spectral profile. Each and every influence requires precise mapping, modeling, and subsequent correction prior to the data being deemed reliable. Globally dispersed teams employ distinct methodologies to independently verify one another's findings. When all data processing streams align on an identical characteristic at the same wavelength, assurance strengthens regarding the signal's authenticity. However, the actual situation here continues to be divided between two distinct origins. Consequently, astronomers adopted an alternative approach, investigating the planet's thermal radiation. When the celestial body passes behind its host star during a secondary eclipse, the stellar illumination becomes the predominant component of the signal. Through a comparison of the spectrum observed prior to and during the eclipse, researchers are able to quantify the amount of light radiated by the planet's sunlit hemisphere. Such thermal radiation provides indications regarding surface characteristics. A substantial atmosphere would effectively redistribute warmth, thereby mitigating the temperature difference between its diurnal and nocturnal sides. Nevertheless, the detected heat corresponds nearly flawlessly with the conditions a barren rocky surface would encounter. The celestial body emits energy akin to a heated, solid surface possessing minimal insulating properties. While this does not entirely preclude the presence of an atmosphere, it constrains it to one that is exceptionally tenuous. Despite this, even a slender atmospheric layer can possess considerable importance, as trace gases hovering above the intensely hot surface are still capable of interacting with stellar radiation during a transit event. Even a pressure of merely a few microbars, which is thousands of times lower than Earth's atmospheric pressure, is sufficient to generate a discernible absorption line, provided the gas comprises the appropriate molecular composition. Should volcanic fissures or warmed minerals persistently emit water, even in minute quantities, the planet might present an atmospheric appearance to a remote observer for transient durations. It is plausible that Webb recorded one such instance. Certain theoretical frameworks propose that thermal desorption, where water is released from warmed minerals, could furnish vapor at a rate exceeding that at which stellar radiation dissipates it. Under this particular hypothesis, the sunlit hemisphere functions as an enormous furnace. Minerals undergo expansion, emit vapor, and subsequently cool once more as the planet revolves beneath the intense luminosity of the star, causing the vapor to ascend. Briefly engages with light before being carried off into space. Its existence is fleeting, yet it remains perceptible. Alternative theories center on volcanic processes. Should the planet's core remain molten, then pressurized magma reservoirs might expel gases via fissures in its outer layer. Io, Jupiter's volcanically active moon, illustrates the immense power of tidal heating, even on a considerably smaller celestial object, assuming comparable forces are present in this location. Such forces might sustain sufficient internal activity to provide a slender yet uninterrupted flow of vapor. Nevertheless, each atmospheric explanation necessitates a precise equilibrium. The amount of water emitted needs to correspond exactly with the speed at which radiation breaks it down. If too little is present, the signal vanishes. Conversely, if there's too much, the planet's thermal profile would deviate from what Webb observed during the eclipse. The extreme precision demanded by that equilibrium is precisely why numerous investigators favor the stellar hypothesis. It aligns more organically. It demands no extraordinary conditions, merely star spots, which are already anticipated on red dwarf stars. However, the stellar hypothesis simultaneously introduces fresh inquiries. Should water vapor exist within the star's atmosphere, it implies that specific areas attain temperatures sufficiently cool for molecules to persist. This would offer an uncommon opportunity for investigating the chemistry occurring within red dwarfs. Such insights could aid in refining stellar models employed throughout the field of astronomy, ranging from exoplanet investigations to galactic evolution. In this regard, even a star-centric explanation contributes to the advancement of the field. The challenge is not indicative of a flaw in our instruments or theoretical frameworks. Rather, it merely mirrors the universe's intricate nature when observed with sufficient exactitude. What previously seemed like a distinct division between a planet and its star now manifests as a complex, layered interaction of illumination and thermal energy, with each element capable of mimicking the other. The Webb telescope possesses sufficient capability to unveil these intricate details, and by doing so, it has brought to light difficulties that no prior observatory ever faced. While preparations persist for the subsequent series of observations, the system remains in a state of scientific anticipation. The planet orbits its star. Every 40 hours, with each revolution presenting a fresh chance for its atmosphere, or its lack thereof, to become apparent. A star steadily rotates, its surface configurations altering sufficiently to modify the spectrum every month, while Webb awaits the optimal alignment, poised to capture the illumination that will ultimately resolve the question of whether the water signature originates from the planet or the star. This inquiry has already transformed the method scientists employ to examine small celestial bodies. Rocky exoplanets, it appears, are considerably more intricate than initially presumed, and stars exert a much greater influence on the appearance of their planets. Deciphering these interwoven signals represents more than merely a step towards resolving a single enigma. The subtle indication of water serves as a basis for comprehending every rocky planet Webb will investigate in the future, despite all the inquiries this tiny world has provoked. It has already accomplished something extraordinary, altering the limits of what scientists previously considered achievable, a solitary, subtle dip within a spectrum. Its enduring and unforeseen nature has compelled the scientific community to reevaluate the principles dictating rocky planetary bodies, red dwarf stars, and the delicate atmospheres situated between them, irrespective of whether the vapor originates from the celestial body or its star. This finding signifies a pivotal moment. Should it originate from the planet, it implies that a rocky world can nonetheless emit, even amidst intense radiation, and temporarily retain water, suggesting a robustness no theoretical framework entirely foresaw. If it originates from the star, it uncovers the chemical composition of red dwarfs, with an unparalleled level of detail, illustrating that these diminutive suns possess greater complexity and exert more influence than anticipated. In either scenario, the outcome expands the scope of future investigations. This system has additionally evolved into a sort of instructional arena, educating researchers on how to distinguish planetary atmospheres from the ambient starlight, how to decipher signals that are just discernible above background interference, and how to discern when a star is mimicking a planet. These insights will guide how investigators examine the most significant planets, those cooler, more tranquil bodies where life could potentially emerge. Without resolving the complexities presented here, more profound enigmas in other locations would remain undiscovered. Thus, the planet persists in its swift orbital path, a seared celestial body hurtling through its star's intense luminosity, harboring mysteries within the slender stratum where heat, gravitational forces, and illumination converge. Webb maintains its vigil, anticipating the subsequent alignment, the ensuing collection of photons, which will diminish the range of potential explanations and disclose whether the planet or the star is the origin of the signal. Yet, in a certain respect, the resolution already surpasses the enigma itself. This stellar system serves as a reminder that breakthroughs seldom manifest as a distinct, isolated instant. More frequently, it emerges as an obstacle, an inconsistency, an outcome that resists integration with The established, straightforward explanations. It compels scientific inquiry to hone its instruments, refine its hypotheses, and reinvestigate with enhanced perseverance. Within the starlight, the reality continues to reveal itself, and provided Webb persists in gathering those remote photons, the cosmos will continue to present narratives that defy our preconceptions and broaden the scope of what we believe planets are capable of being. Should you appreciate this video, please remember to give it a thumbs up and subscribe. Your support significantly contributes to the channel's expansion.